again, I'm not going to go unless there's 1,000 people. You know, I'm just over it. I can't work under these conditions.
I can't.
Hey Hal, do you have the canned? Do you have a flyer on your class or anything where you have all those things you said? Someone's asking me to say it again. I'm like,
I'll post the link.
So it's on the Wild West Hack and Fest site. We got all the stuff, the laptop requirements, and the what we're going to talk about during the training and all that stuff. So head on over to the Wild West Hack and Fest site and click on the training.
awesome.
Head on over to the Wild West Hack and Fest site. We're on the training. Sorry, I haven't had
anything. Like, it's shocking.
I was expecting you to get up and start square dancing, maybe with Sadplane.
I can't make this window go away on my laptop, and so
Can I mute that?
I feel like I've never used a computer before right now. All right, Hal, you have 1 minute. You okay? You good?
I'm excited. I'm ready, man. Let's do it.
All right. Is now a good time for the bathroom break?
Now's a good time for the bathroom break right now. Like when you're boarding the plane with children. Okay, we're now boarding zone 1, and the kids are like, I have to go to the bathroom. It's like,
It's a 2.
It was 2 weeks ago. Tim Medine, like 2 minutes before it starts, just like walked out of frame, and I was like,
that's
he came back and he's like, I had to use the bathroom. I didn't want to say anything. Why wouldn't you
there
say
goes.
Yeah. All right, Hal, your audio working?
Ready.
Video's working? All right, John, I'm going to have you introduce. I'm going off camera. John, can you introduce Hal? Okay, so John's microphone's not working, so I'm going to introduce Hal. It's not working.
The demo god strike.
So hello, everybody. It is 3 p.m. Eastern time, and we're here with Hal Pomeranz and John Strand, apparently.
And an oddly silent John Strand. So,
Thank you for being here for our next Black Hills Information Security webcast. Today we have Hal Pomeranz. He's returning for more Linux goodness. He's got the Linux Forensics Magical Mystery Tour. Hal's been with us a few times. If you've missed his previous webcast, if you check the recordings channel inside Discord, you can find it there. And then just to let you know, if you have questions, try to direct all questions to Discord. But if you're not in Discord, you can still ask them in GoToWebinar. We have a team of people to help answer questions in GoToWebinar and in Discord. So regardless of where you ask. But if you ask them in Discord, it's just better. And then with that, Hal, I'm going to...
Wait, I have an exception to that.
Okay.
You've got a great question for Hal to answer for the whole community. Get that into GoToWebinar.
Yeah. All right, Hal, it's all yours.
all right. Thanks, guys. Nice to be back again. We sort of took April off, but here we are in my May overexposure tour. We've got some training coming up with Black Hills on Linux forensics, and I wanted to use this little 1-hour webinar to talk about some stuff that's not in that training. It was a couple of items that came up as kind of technical tangents during the training I gave at KernelCon, and I thought it would be nice to, go over them and have them recorded so they could go up on the Black Hills YouTube channel and everybody could kind of benefit from those off-book discussions. So I guess a quick intro. For those of you who don't know me, my name is Hal Pomeranz. I've been around for a while. I started as a Unix systems admin back in the 1980s, and the world was a very different place, and Linux didn't exist, and dinosaurs roamed the earth and things like that. I've been running my own consulting business for more than 20 years now. These days, my consulting practice is all about forensic investigations, expert witness work, incident response, and so on. because I'm kind of a lone eagle, I tend to loan myself out to various professional services groups for surge staffing kinds of things. So you might see me showing up working for various different companies, depending on whether you're lucky enough to engage with us. And I guess I'm kind of known for doing Linux forensics, so I probably catch more Linux investigations than the average forensics professional. But I admit to doing Windows and Mac as well. There's my contact info, so if you have any questions after the webinar is over, please feel free to reach out, and we're happy to answer your questions. Okay, so what are we talking about today? So I wanted to talk about some topics in the Linux EXT file system, ext4, which is the most recent version. Now, look, ext4 is really just the most modern incarnation of what's actually a pretty old file system. The original Unix file system from the 1970s evolved into the Berkeley Fast File System in the mid-1970s in 4.2 BSD. And it was that 4.2 BSD fast file system that really was the basis for the common Unix file systems that you find in all sorts of different Unix flavors, right? So, it's FFS on BSD, it's EXT on Linux, but it's UFS on Solaris, and, so on and so forth. So this is, pretty much the standard Linux and Unix file system. And there are still, huge portions of this file system, on-disk data structures and the way the file system works, which are really just based entirely on Kirk McCusick's original design for 4.2 BSD. And then extra features have been added since then. And what I find interesting, and where I think there's sort of opportunities for exploitation, for want of a better word, are where the old stuff meets the new stuff. And there's some interesting interactions there that I just wanted to talk about in this little 1 hour webinar. Okay, so the focus is ext4. A lot of what I'm going to be talking about, though, applies to other variants of the Unix file system. But if you're talking about, ZFS or XFS or some of the other file systems that you find on Unix and Linux systems, that's a whole different conversation. Okay. All right. So let's start with something that is pretty straightforward, at least at first, right? So Atime updates, right? So Atime, last access time. Now, in traditional file systems, the last access time on a file would be the last time you viewed the contents of the file. Or like if it's an executable, it usually represents the last time you ran that program. And, for many, many years, file systems did what we call strict Atime updates, right? So every time you read that file or every time you executed that program, it would update the last access time, the Atime on the file. And that was a useful forensic artifact because it, would, for example, tell you the last time a particular program was run on the system. Now, of course, Atime updates were always very ephemeral, and there were problems with things like virus scanners that would run over your entire file system and update all of the Atimes. But, other than that, Atimes were a useful indicator for access to files. But what they were not was efficient for file systems, right? If you're saying that I have to strictly update the Atime every time I read the file, that means that every file read operation turns into a write back into the file system, right? I have to update the inode with the new Atime information. And that sucks from a file system performance perspective. And so various file systems stopped doing Atime updates just for reasons of efficiency. For example, Windows NTFS, starting in Windows 7, the default was not to do Atime updates at all. They were just essentially frozen, at the time you created the file. Now, you could change that default. You could switch it back to the old strict Atime update behavior. But the default going forward, from Windows 7 forward, was that Atime updates weren't going to happen. Linux systems did something a little bit different, and it's weird. And so it was one of these topics that came up, and explaining how Linux does Atime updates always kind of boggles people's brains. So I wanted to do a little bit more explanation about this. So rather than strictly saying, we're not going to do Atime updates, which is the direction Microsoft went, the Linux people said, no, we're going to do this thing which we'll call relative Atime updates. And so the rules for relative Atime updates are the Atime will get updated if the file is being accessed and the current Atime is less than the last modified time of the file. So it's relative in that sense, right? We're only going to update the Atime if it's older than the last modified time on the file. Why do you care? Well, okay, so the reason Unix people care about this is for things like Unix mail readers, where you want to know if the person has accessed their mailbox since the last time the mailbox was updated with new email, right? And so Linux systems actually care very much about the relative relationship between the Atime and the M-time, right? So the goal for relative Atime updates was to make sure, we weren't going to update the Atime every single time because that's inefficient. We just needed to update it if the last modified time was bigger than the Atime. Oh, also though, and here's the catch, there's another part of the relative Atime updates, which is Atime updates will happen if the Atime hasn't been updated in the last 24 hours, right? So, the idea is that we'll sort of update the Atimes on a daily basis if necessary, or if the Atime is less than the current M-time. So that's relative Atime updates. Now, so the weird thing about this is it changes the meaning of Atimes in your forensic analysis, right? We used to use Atime updates to say, oh, look, that was the last time somebody looked at that file, or the last time somebody ran that program. But now, with these relative Atime updates, which are infrequent, what it usually ends up happening, and the usual interpretation of that Atime update, is that it's actually the first time that program is executed in a certain interval, right? And to show you that, let me just give you a quick demo here, okay? So let's see, we've got a program like that wouldn't commonly be used, right? debugfs, okay? So the attacker on your Linux system is going to use debugfs to reset timestamps on files and directories in the file system, right? Now, debugfs is not a command that's commonly run, so you wouldn't expect the Atime on that file to have been updated very recently, right? So let's see what the current Atime is on debugfs. Oops. Okay, so let's see. The last time I ran debugfs on this system was 4 days ago. All right, so May the 3rd. Cool. Now, that Atime update is larger than the last modified time, but is more than 24 hours ago. So if I run debugfs right now, it's going to set the A time to be the current time that I run the executable. So let me just do a little debug fs. I'm not even going to issue any commands. I'm just going to quit out of it. Right? Okay. And now, if I stat the debug fs program, you'll see, look, we've just updated the A time. My clock's a little out of sync here, but you get the idea, right? So my running the debug fs command just updated the A time to the time that I ran debug fs, because I hadn't executed it for more than 24 hours. Now, if I go back, though, and I run debug fs 100 more times in the next 24 hours, those won't register in the A time, right? So if I run debug fs again and quit out, you can see it's the same value from the first time I ran debug fs here, right? So that's what I mean about the A time with relative A time updates in Linux, indicating kind of the first time that program is run, right? So I had a case where the attackers broke into the system and they started running a bunch of commands that were not in the typical list of commands that the systems administrators on the system would run. And I could see, with the A times on those executables, exactly the order in which the attacker ran those commands for the first time. Right? And because some of the commands also created log messages in the system logs, you could correlate those timestamps with the log messages in the syslog logs as well, to get corroboration on that. So yeah, so with relative A time updates, you're thinking, oh well, A times aren't getting updated all the time, therefore they're not useful. No, they're useful. They're just useful in a different way, right? So rather than being the last time the attacker ran the tool, it's within a 24-hour window, it's the first time the attacker ran that tool or accessed that file. And that's still useful information. So, unfortunately in Unix, there's no prefetch equivalent like there is in Windows. But, at least as an indicator of the first time somebody ran the program, it's still useful. So that is relative A time updates. And it's one of the things that people find confusing because it's so incredibly Linux specific, and it's not something that happens in a lot of other file systems. Cool. Now, the other thing that I got a lot of questions about when I was doing my Linux forensics training for KernelCon was questions about recovering deleted data. And, there is a huge body of stuff that I want to add in the next iteration of the course, which is file system internals for EXT and XFS, recovering deleted data, and all of that. But, we just didn't have time in the 2-day format to put all that stuff in. I mean, that's easily 2 days of material by itself, and that's if I leave out a lot of detail. So yeah, I'm hoping to do another iteration of the course that dives into that stuff in more detail. But I did want to talk a little bit about my strategy for finding and recovering deleted data in Linux EXT file systems, because it's not straightforward due to some design choices that the Linux developers made. All right, but let's talk about some basic stuff. Okay, so this is another one of these weird things that comes to us from the early days of the Unix file system, which is the way directories are structured in Unix. So, and I'll get to why this is important for recovering deleted data in just a sec. Okay, so if you look at a directory in Unix, the classic Unix directory structure is simply an unsorted list of these records, okay? And for each file in the directory, there's one of these records, and you can see the record format documented on this slide. So the record starts with 4 bytes, which is the inode number associated with the file. Then after that, there's a length field, which is 2 bytes, which says how long this entire directory entry is, including, by the way, the inode number that came before it. Now, the directory entries in Unix directories need to be 4-byte aligned, right? So whatever the length is, it's always going to be 4-byte aligned. After the 2-byte length field, there is 1 byte, which is the actual length of the file name. And then there's a 1-byte file type, which is actually redundant with information that's stored in the inode, but it's there so that, for example, when you do ls-F, it can show you the little indicator to tell you what type of file it is without having to look at every single inode. So there's a 1-byte file type field there, and then there's the file name. And if the file name doesn't consume all of the space in the 4-byte aligned length, then there's just null bytes at the end of the record to pad it out to a 4-byte alignment. And the records are unsorted. Basically, the way this works in Unix directories are that the records are added in the order the files are created. They're not in alphabetical order, they're not in anything, right? It's one of the classic issues with Unix directories. When you add more files to a directory, your average seek time to find the file you're looking for increases linearly, right? So as Unix directories get fat, like human beings, they tend to slow down, right? Okay, so what I'm going to do is I'm going to make a directory here, and I'm just going to show you this structure real quick, and then we're going to delete a file, and we're going to see what happens, okay? All right, so let's see. I'm going to cd over into my images directory, and I'm going to make a directory called test directory. And in this directory, I'm going to create a bunch of files. These are some new files. Okay, so I'm just going to create 5 files. Okay. And when I do a directory listing, you see the file names in alphabetical order. But if we were to actually look at the contents of the directory, what you're going to see is that the files were actually added to the directory in the order I expressed them as arguments for the touch command. So I'm going to dump the contents of this directory. Linux is a little persnickety about showing you directory contents. You can't just easily hack the directory. Linux says, no, that's not allowed. So I'm going to use a little bit of lower level forensic magic with the sleuth kit to dump out the directory. So let's see here. ls-i dot, give me the inode number of the current directory. Of course, I want to do the D flag, so it shows me the inode number of the directory and not the directory contents. I meant to do that. All right, so inode number 7864321, right? Let's icat that file system and show me the contents of the file, the directory, at that inode number. And I'm going to pipe it into XXD so that we can see a hex dump of it. And then we'll just look at the first 10 lines or so. Okay, so here you go. Here are the contents of the directory. Okay, so remember the format of the records, right? So 4 bytes with the inode number, okay? And then a length byte, which is the total length of the entry, including the inode. So this entry is going to be 12 bytes big. Remember, it's going to be 4-byte aligned, right? So 12 bytes. Okay, and then so the length field is actually these 2 bytes, little endian. Right? Okay, and then the file name length, which in this case is 1 byte, and then the file type, 02, means it's a directory, and then the remaining bytes, well, there's only 1 byte for the file name, 2e is dot, right? So this is the dot entry. Okay? And then the remaining bytes, which are unused, are just padded with nulls. Okay, so this whole thing here is the 12-byte directory entry for the dot link that always appears in the directory. The next one is the dot link. You can see here 2e is the file name. Okay. And then starting right here is the first file name. So let's see, we've got 4 bytes of inode right here. We've got 2 bytes, which represent the length of the entry. So 10 x 16 bytes, right? Then we have a length of file name byte, so 5 characters in the file name. File type 1, regular file. And then these 5 bytes are the first file name, which is the word these. And we've got some garbage here. That's interesting. Yeah. Okay. So there's a little bit of extra characters in here. So you can see the word these, and it's followed by LE. What happened there? Interesting. I'm actually, I'm sort of curious where the extra characters come from.
You're getting a lot of comments on Discord of
Yeah,
people trying to help or give advice.
Well, interesting. We'll go back and research that one. In any event, so you can see the first file name is these, and then here's R, some new files. And I think what's happening here, to be honest, is I've picked up a block that I've used before for a similar demo. And what you're seeing here, what you're seeing here is essentially directory slack, right? The characters after the file name are just junk. They're not zero filled. They're just slack space that's unused. And so what you're seeing is remnants of previous content in this block. Because even after the 5 file records, you can see that there's additional records, right? So here is the 5th file I created, right? Files, this one here that I've got highlighted. Okay, so let's work backwards a little bit from that. So this is where that file name begins with the 66, right? So 66, 69, 6C, 6573, right? That is the word files in ASCII. Okay. All right, so that means that this 2 bytes here, this is the file type, 1. This is the length of the file name, 5 bytes. Okay, so that means that this large value here is the total length of the entry, right? And you'll notice that it's quite a large value. It's FB4, if you read that, in big endian notation. And that basically consumes the rest of the block, right? So what you're saying is that this is basically the last entry and that all of the rest of the block is slack space. And I do that first to prove you that what we're looking at here is slack from a previous block. But it's also relevant because this is fundamentally how things work when you delete data from a directory as well, okay? So let's say I'm going to delete a file name. I'm going to delete one of these file names that are in the middle, okay? So I'm going to delete the sum file. So I'm going to rm sum. Okay, so what happens in the directory when I delete that file? Okay, and this is one of these peculiarities of Unix directories that it has been around since again, the early days of the fast file system in 4.2 BSD. When you delete one of these files from the directory, the file record in the directory file is unchanged, right? The data in that record for the file sum is unmodified. What happens is the record before that record, in this case, the record for the R file, grows to consume the space that used to be occupied by the record for the sum file, right? So what happens is the previous directory's entries length field is increased by the size of the record for the deleted file. And so the result is all of the information about the deleted file, including file type and INO number, are still visible in the slack space, what is now the slack space of the active directory entry right before the thing that got deleted. And you can see that if I do the same icat command, right? Okay, so you can see here, just like in the ASCII interpolation, right? Nothing's different, right? And if you look at the hex closely, right? So here at the beginning of this line, right? Okay, so here's ARE, right? So, ASCII ARE, the name of the file. Okay, so, and so on the line before that, you see the file type, regular file, and you see the, length of the file name, which is 3 bytes. And then right before that, you have the 2 bytes, which are the length of the entry. So in this case, the entry length is now 24, right? If you were to look up above, right, at the previous entry length before I deleted the file, it was only 12, right? You had, the ARE and then nothing after it. But now the length has grown to consume the now deleted file record, right? So here's sum, right? And you can see that, here, the length of that record for the file sum was 12 bytes, okay? So when we delete the 12-byte record for sum, then what happens is the length of the R record grows to be 24 bytes, and it consumes the space that used to be occupied by some. But you can still see the original record for some, right? Here's SOME in ASCII. Here's the file type. Here's the length of file name. Here's the original record size for that now deleted record. And here is the inode number, right? Okay. So that's great because it means that when a file is deleted in Linux file systems, or pretty much any typical Unix file system, the deleted directory entry is still there, still visible. You know the inode number that used to point to that file. And that can make file recovery very straightforward, right? You're like, oh, cool. I know the inode number. I can use the block pointers in the inode to pull back the file, and life is good, right? Ultimately, that space for that deleted directory entry may get reused, right, by some new file. But until that happens, you still see all of the properties of the original file, including its original inode number. Like, awesome. Okay, great. I can look through the slack space in directory files, and I can see the inode numbers associated with the deleted file entries, and I can then use that inode and the block pointers in the inode to pull back the deleted file, right? And yeah, up through ext2, that tactic totally worked. But unfortunately, starting in ext3, they started zeroing out the block pointers in the inode for privacy reasons, right? When you deleted a file, they wanted to make it people to pull back the contents of the deleted file. So as a design decision in ext3, they decided to zero out the block pointers in the inode when a file was deleted. And the same thing is true in ext4. When a file is deleted in ext4, all of the extent information in the inode is zeroed out. And so, yes, you can see the inode number that was originally associated with the file as long as that deleted directory entry persists, but recovering the file contents is now impossible because there's no block pointers information left in the inode. Well, that sucks. So really that inode number in the directory entries not helpful to us, right? Yeah, maybe it is. So the answer is actually no, that inode information might be useful. But to understand why it's useful, we need to have a little technical digression and talk a little bit about how file allocation happens in Unix file systems. So I promise I'll get back to recovering deleted data in a minute, but let's talk a little bit about file allocation. Okay, so you look at a Unix file system, and the way the blocks in the file system are organized are in terms of these things called block groups. So basically, the Unix file system divides all of the data blocks in the file system into these block groups of 32K blocks per group by default. And within a block group, you're going to have some of the blocks that are dedicated to inode storage and some of the blocks that are allocated to data blocks. The idea behind the block group strategy was to make it so that the inode structures, the metadata about the files, was close to the file content for efficiency. In the original Unix file systems, there was a metadata area at the front of the disk where all of the inodes were stored. And then the rest of the disk was data blocks. And that didn't matter so much when you were talking about a 5 megabyte RK05 disk pack, right? But as the file systems got put onto larger and larger disks, hundreds of megabytes, and even gigabytes, it was a problem that the metadata was now far away from the actual data blocks. So one of the innovations in the fast file system was this block group idea where you would group together chunks of inodes with chunks of data blocks. And so if you look how this is organized at the, in any particular block group, you're going to have a bitmap which tracks which blocks are used and which inodes are used. And then there's going to be some number of data blocks that are associated with inodes. And then the remainder of the block group is just going to be used for data blocks. And actually, you can math this out. It's very predictable. So each of the bitmaps, the block and the inode bitmaps, occupy a single block in the file system. Now, in Linux EXT file systems, the default block size is 4K. So 4K bytes, if each bit represents a block, that means you can track 32K blocks with a single 4K bitmap, right? That's why the size of the block group is 32K blocks, because they use a 4K block to track each block with a single bit, right? So 4 times 8, 32K, there you go. So the block bitmap tracks each individual block with a bit, on or off, depending on whether it's allocated or not. Now, the standard Unix file system uses a ratio of 1 inode to every 4 data blocks. You can change that when you create the file system, but the default ratio is going to be, there's going to be 1 inode to every 4 data blocks. So that means that in a given block group of 32K blocks, there's going to be 8K inodes. Okay. Now in ext4, each inode is 256 bytes. Okay. That means 16, do the math right? Yeah, 16 inodes. No. Yeah, that's right. 16 inodes per data block. Okay. If there are 8K inodes, that means you need 512 blocks worth of inode storage. And then the remainder is going to be data blocks. Okay. So that's why there's going to be 512 blocks worth of inodes, by default anyway, in the block group. Now, the block group may also contain backups of the super block and this group descriptor table, which says where the block groups are on disk. So some of the space at the beginning of the block group may also be occupied by file system metadata. That file system metadata is scattered on basically on cylinder boundaries throughout the file system for redundancy. And you can see this. Let me pull up another sleuthkit tool here for you. I'm going to run fsstat on my dev SDB1 file system here, and it will actually show you the block groups. Okay, so look, it's an ext4 file system, yada, yada, yada. You can see the number of blocks and the number of inodes. You can see the block size. It's the 4K default. And if you eyeball this, you can see there's roughly 1 inode for every 4 blocks, like I said. Okay, and then so after the basic block and inode breakdown that you see in the super block at the beginning of the file system, you then see the breakdown of all of the different block groups. Okay, so there's 1,491 block groups with 32K blocks per group and 8K inodes. per group. So here's group 0, which starts with the first block. And so, the blocks range from 0 to 32K. The inode range is, this inode number, so inodes 1 through 8K. And you can see the layout of the blocks in the block group here, right? So this is block group 0. It's right at the front of the disk. So the first block is going to be the super block. The next several blocks are the block group descriptor table, which describe where all the block groups live on the disk. And then there's reserved space. If you extend the file system, you're going to need to grow the block group descriptor table. So there's a lot of reserved space for growth, probably more than there needs to be, honestly. But I guess they believe in future proofing. Here's the block, which is the bitmap, which tracks whether the data blocks are allocated or not. And then here's the block, which tracks whether the inodes are allocated or not. And then the inodes themselves, and then the data blocks, and off you go. So that's group 0. And then group 1 starts right afterwards, right? So group 1 picks off with, the next range of inode numbers and the next range of blocks. And block group 1 also has a backup of the super block and the group descriptor table, and then the data bitmap and the inode bitmap, and then the inode blocks, and then the data blocks. Okay, and then here's group 2. Now, group 2 doesn't have a backup of the super block or the group descriptor table, so it just starts with the data bitmap and the inode bitmap, and then inodes and data blocks, and so on. And then here's group 3. Oh, look, there's another backup super block in group 3, and then the group descriptor table, and so on. The backup super block and the backup group descriptor tables get progressively more sparse as the file system goes on, right? You don't want to waste a huge amount of space on all of these redundant copies, which you probably were never going to use anyway. So, why am I going into so much detail about these block groups? Why do you care? Why you care is once you understand the allocation strategy for Unix file systems, these block groups help you find the deleted data you're looking for. Okay, so let's talk a little bit about the allocation strategy for Unix file systems as it applies to this block group. Okay, I'm going to create a new directory. I just created a new directory, my test directory, right? When you create a new directory in the Unix file system, it is placed in the least heavily used block group. And if the file system is relatively lightly used, there's probably multiple block groups that don't have any data in them. So the file system just picks one of those block groups more or less at random, and that's where your new directory is going to sit. And then as you create files in that new directory, those files are created in the same block group, at least until that block group fills up, right? And again, this is done for efficiency, right? If you're going to do like a directory listing, chances are the next thing you're going to do is you're going to look at the contents of one of the files in that directory. So it was convenient to have the file content near the directory information itself. Okay, and you can see this actually in the directory that I created, right? You'll notice that, let's see where I did the ls-i. Okay, so you can see here, look at the inode numbers for the files that I created, right? Remember I created these are some new files, right? So these got inode number 322 are inode number 323, some inode number 324, new inode number 325 files. 326. Oh, and by the way, you'll notice that the inode number for the directory itself is inode number 321. So we got sequential inode numbers as I created files in this directory. So clearly, all of those inodes are all in the same block group. And in fact, the blocks that would be used by the files would also be in the same block group. Now, those are zero-length files, so there's not going to be any data blocks associated with them at the moment. But you get the idea, right? So when I create a new directory, that directory is placed into the least recently used block group, and then, the least heavily occupied block group. And then any files I create are placed into the same block group to keep sort of locality of reference. By the way, this is also the reason why once Unix directories get big enough to occupy more than a single block, they fragment, right? Because think about how the directory is going to grow. I just created this new directory. It consumes one block. I put some files into it. The inodes and the data blocks that are used by those files are going to be the inodes and data blocks that immediately follow the inode and the data block used by that directory, because they're all in the same block group. And for efficiency, it's just going to use the next available blocks and inodes, right? So once you've added, hundreds or thousands of files to the directory, and it grows to a point where it needs to be bigger than a single block to hold all those file records, the next block after the original block for the directory is going to be occupied by some file content from the directory. So I'm not going to be able to expand the directory without fragmenting it. So Unix directories fragment and they get big too, which is actually a real hassle for recovering large directories, as it turns out. Just FYI. But in this case, this locality of reference thing is actually a good thing for me, right? Because, I can see in the deleted directory entry the inode originally associated with a given file. And I can then use that inode number and figure out what block group that inode was part of. And it's usually the case that the data blocks associated with that file are going to be in the same block group. It's the inode. Okay? So what that means is, it might be a multi-terabyte disk, but chances are the content that you're looking for is in that 32K block group, right by that inode. And that can save you massive amounts of time when you're recovering deleted data. Let's look at a practical example, okay? All right, so I'm going to show you a disk image that I use in my Linux forensics class. And if you take my 2-day Linux forensics training, we're going to have a lot of fun with this disk image. It's a disk image of a hacked web application. The disk image was put together by Ali Hadi and the folks from Champlain College, the forensics program there. They were kind enough to let me use their disk images in my class, so I appreciate that very much. And I always like to throw a shout out to the Champlain folks for providing those disk images. Okay, so let's take a look at a particular directory that I know is interesting in that disk image, which is the temp directory from the disk image. So I have the disk image mounted up in my forensic workstation here already. And so, and I want to look at the contents of the temp directory. Okay, so I'm going to get the inode number for the temp directory. It's mounted up under mount test data /tmp. All right, so here's the inode number of that temp directory. I'm going to use another sleuthkit tool called FLS so that you can see more clearly the deleted entries in /temp. And we're going to talk about one that might be interesting to us. Okay, so I'm going to FLS, what is it, dev mapper. So I'm going to FLS that inode number from the file system that we're looking at. And the starred entries are deleted entries. So this file right here, this Apache, some random collection of letters, that file is still in the directory. Like if I listed the directory, you would see that file. But all of these other starred entries, those aren't there anymore. Now the sleuthkit recognizes them as deleted directory entries, but they're not there. And so, I mean, there's all kinds of interesting stuff here, right? There's a couple of deleted zip files. You know, there's a shared object. There's a shared library there, right here, right? But I'm sort of curious about this .c file, right? Oh, you know, I love it when attackers bring source code onto the system, right? And I'd like to be able to recover that deleted source code. Okay, now we can see that the inode number that was associated with the .c file is this one right here, 1177375. Okay, let's find out what block group that inode number was associated with. Okay, so I'm going to istat dev mapper.
5 minutes, Hal.
I'm not stopping at 5 minutes.
We have post open, or don't worry about it.
Yeah, we're having fun. We're recovering deleted data. All right, so I'm going to istat that inode number. And so it tells me that that inode number is in group 144. Okay. Okay, so let's take a look at the fsstat information about that block group. So fsstat dev mapper root, and I'm interested in group 144. Oh, let me give you some context around that. Oops. Oh. Nope. Okay. Do it the old-fashioned way. Oh, it's just group. There we go. Okay, so here's the information about group 144. You can see the inode range, right? And that inode range definitely includes 1177375, right? Starts at 1177345. So we're definitely in the right block group. Okay, so the blocks in that block group, you can see the block range here. Okay. So what I'm suggesting to you is that the blocks in that .c file are likely to be in that range of blocks. So how do I see just that range of blocks? I'm going to use the dd command. dd, my input file is the file system in question. Oops. My block size is 4K. I am going to skip that many blocks, and I'm going to count 32K. And I'm going to grab 32K blocks starting from that point. Right? And I'm going to save that into a file, which I'm going to call images block group 144.raw. Right? So I am just carving out those 32K raw data blocks. So I'm using DD like a Ginsu knife to slice out the blocks that I want. Now that .c file, that's just going to be text, right? So I'm going to be doing some string searching to find the source code. So I'm going to run strings on the raw data that I just pulled out. So I'm just pulling out the ASCII strings. The -TD means give me a decimal byte offset where that string starts in the block collection. I'm going to call the strings bg144.ascii. All right, so I've ripped out all the ASCII strings. Now, what's a good string to look for? If you're looking for C source code, my favorite is pound include, right? Pound include is always going to be there in a C program, C++. It's always a good string to search for. So I'm going to fgrep for pound include from my ASCII strings. Ooh, bummer. So what happened? Was I lying to you? Well, I said that you tend to find the blocks in the same block group as the inode. But what if all the data blocks get used up, right? There are a lot of deleted files in this directory, right? What if they filled up the temp directory, the block group 144, not leaving any data blocks? Oh, the answer is then it rolls over into the next block group. So let's try block group 145, shall we? All right, so show me the blocks associated with group 145. Okay, and there's that list of blocks. And I'm going to basically do the exact same thing I did to extract block group 144, except I'm just going to use different parameters. So same DD command, except that now I'm going to skip to the beginning of block group 145, and we'll call the output file block group 145.raw. And again, I'm going to run strings to extract the strings from our block group 145 data. And we'll do the exact same grep command again on the data from block group 145. Woot, there it is. I mean, if anything screams exploit, it's this particular line. But you can see multiple pound include statements. So, all right, so what is this number? Okay, that number is the byte offset to the beginning of this string in our block group 145 collection. Okay? I want to know the block number, because I want to see the whole block. So to get the block number, I just do math. I'm going to divide that byte offset by the block size, 4K. So this is going to be in the 470th block in the block group collection, block group 145. Okay. I'm going to use DD again. DD. Now my input file is the block group 145.raw file. Block size is still 4K. I am going to skip 470, right, to get to the block I want to see. And I'm just going to let it dump out to the standard output. So count equals 1. I just want to see the 1 block there. So, it's the overlay FS privilege escalation, and they actually got it from exploit DB. This is the exploit DB header. For those of you who've never seen this before, it tells you like how to use it and so on and so forth. Here's the code. Here's the statement that I was looking at in the string search. Nope, but it looks like that wasn't all of the exploit, right? We're clearly truncated. We've reached the end of the block, but not the end of the exploit. Okay, let's look at 2 blocks, right? Oh, there's the end of it. Okay. So in 2 blocks, starting at block offset 470 from the beginning of the block group, here's your .c file, and here's your exploit, right? So I didn't have to search the entire disk. I just had to search the block groups around the inode associated with the deleted file entry. And I found my exploit. And that saves you a huge amount of time on big disks, right? So there you go, recovering deleted data in a Unix file system using deleted directory entries and what we know about file allocation strategy for Unix file systems. It's not magic, it's just knowledge. Woo, that was fun.
That was awesome.
You got a record, Hal. You got a record. Longest. That's awesome.
Thanks for listening.
Yeah, are we gonna even try questions here?
Yeah, hell yeah. It's just post-show banter.
Yeah, post-show banter. So I'm going to kill the recording. Thank you all for being here.
Are there any questions about what I just did before we...
Yeah, shit ton of questions, Hal. Like, how do I get my doctorate in disk geometry, baby? How do I do that?
Say again?
How do I get
How do
my
you get the
doctorate in disk geometry?
How do you get the disk geometry? You mean like where the partitions are laid out and stuff like that?
No, I'm just saying there's so much stuff there. It was...
I mean, this gets really deep really fast. So let me say, for those of you who want more detail about this, if you go to my personal webpage, dear-run.com/Hal, there's a link to a material I wrote, probably 10 years ago now, looking at the internals of ext4. And I wrote that up for the SANS Forensics blog. So you'll find it there. And I go into a heck of a lot of detail about all this stuff. If you're interested in XFS, I got started writing up a similar set of documents, also linked from my personal webpage, about XFS internals. I got interrupted in the middle of finishing up that series. I wrote like 5 or 6 articles. There's still more to write, but then I got interrupted by some casework and I never went back to it. But I will, I promise. Anyway, so there's more stuff about XFS internals on my Righteous IT blog. So there is more information. And of course, there's Brian Carrier's book, File System Forensic Analysis, which is also really important for this discussion as well.
Somebody asked about that, a good book on it. So that's awesome.
Yeah. So the Brian Carrier book, File System Forensic Analysis, So it talks about Windows, Mac, and Linux file systems up to ext3. And then, so my ext4 work was basically designed to be kind of a follow-on to that, to cover what's different about ext4.
What are they? What's Macintosh using right now?
So, I mean, so in Carrier's book, it talks about HFS Plus, which was the old Mac file system. The new Mac file system is APFS, which I gather there was basically an errata that was put out for a file system forensic analysis that talks about APFS. Also, Sarah Edwards has written a lot about APFS. So you can look for her stuff as well.
Awesome.
Yes.
She's a rock star too.
Yeah, I was reading on social media, somebody was doing a forensic challenge that involved Mac forensics. And they basically said, God damn it, like 90% of what I'm Googling is all written by Sarah Edwards. It's just like everything Mac related is Sarah. It's unbelievable.
All right. Well, so what we're going to do now is just kill the recording and stick around a little bit for some questions. And then, but thank you so much for being here for this Black Hills Information Security webcast. If you need a pen test, let us know. If not, that's fine too.
Forensics,
And,
let me know.
yeah.
Yeah.
And we'll see you next.
Talk to Hal.